In this video, we're going to talk about titrations in a little bit more detail and see if we can figure out how we can determine the equivalence point experimentally. In the last video, I gave you a quick overview of titrations as an experimental technique. In this video, we're going to talk more about how titration can be used as an accurate and precise analytical technique. If we look back at Chang's definition for a titration, it raises the question, how do we accurately know the concentration of the forced solution? In most cases in our lab, we're going to use a primary standard to accurately determine the concentration of our known concentration solution. This is a substance that is stable at room temperature, is easily dried, will not readily absorb water, and its mass can be accurately determined. When determining mass, we consider accurate to be out to the plus or minus 0.0001 grams or 0.1 milligrams. This is where it becomes important that you write down all of the values from the balance into your lab notebook and report all of the numbers when you're doing your calculations. We will then use mass and our knowledge of stoichiometry to convert from mass to moles. So hopefully you're asking yourself, why can't we simply use sodium hydroxide as a primary standard? Well, the short answer is that it doesn't meet this criteria. Which criteria does it not meet? So the standardization process will involve accurately measuring the mass of a primary standard, in this case potassium hydrogen phthalate or KHP, using the analytical balances. We're then going to titrate a solution of KHP using sodium hydroxide. We do this to accurately and precisely determine the concentration of sodium hydroxide. Once we know sodium hydroxide's concentration, we can use it to titrate the solution of acetic acid, whose concentration is unknown. Remember, at each step, we must use the balanced chemical reaction to determine the moles of H+ ion and hydroxide ion in the solution. In the previous video, we explored how to calculate the concentration of a solution whose concentration we don't know using the equivalence point. Remember, the equivalence point is when the moles of hydrogen ion equals the moles of hydroxide ion. Or, to put it another way, when the moles of acid are stoichiometrically equal to the moles of base. So the question then is, how do we produce the graph? Well, we can set up the apparatus easily enough by following the procedure outlined before, then fill the burette and put our unknown in the beaker. The question then remains, how do we know when we mix the two clear substances together when we reach the equivalence point? Experimentally, there are a couple of different ways to do that. One method we discussed briefly in the other video is using a pH probe. The pH probe takes real-time pH measurements and sends them to a computer, which will automatically correct the plot. The other option is using an indicator. An indicator is a substance that changes color based upon pH. This allows us to visually determine the equivalence point as we manually observe and record the volume of titrant added. But first, let's do a quick review. When we say pH, what do we mean? pH refers to the measure of hydrogen ions, H+, in a solution. As you increase the amount of hydrogen ions, the lower the pH becomes. Therefore, an acid, which releases hydrogen ions, has a solution with a higher concentration of hydrogen ions than water, and a base, which releases hydroxide ions, has lower concentration of hydrogen ions. The pH scale, as in the one shown, ranks the solutions based upon how acidic or basic they are. This image shows increasing acidity and basicity, otherwise known as alkalinity, comparing everyday things that we would see in our household, such as lemon juice or milk, and many things that we hope not to see, like acid rain. We use pH indicators to help give us an idea of what the pH solution is, therefore telling us how acidic or basic the solution can be. pH indicators come in many types, such as pH strips, like shown there on the right, which change color once they touch the solution. You also can have chemical pH indicators, which change color to allow us to visually determine the pH. Phenolphthalein is an example of an indicator that changes color at a particular pH. If you look at the chart on the left, you can see a general idea of the color that you expect to see as it changes. For phenolphthalein, it goes from clear at a more acidic pH to a more hot pink at a more basic or higher pH. The ideal spot for phenolphthalein is that lighter pink color in the middle, which is about pH 8 to 9, which is where the equivalence point will be. Don't worry, you don't need to memorize the information in this table. However, you will need to be able to interpret information provided like this to determine what a good indicator would be for a titration that would have an equivalence point at various pHs. Remember, if you have any questions, please make sure to ask them on our Course Piazza site, reach out to your TA, or ask somebody during office hours. Thanks.